All right, thanks. Thanks to Chris and Aaron for inviting me to be a part of this. I'm also from Southern Illinois, from Hamilton County originally, and I'm the regional engineer for NRCS for the bottom 30 counties in Illinois. So that's the area I cover. Me and 6 other folks. I have some other engineers and civil engineering technicians on my staff. And I've done that for about 32 years now. So I guess I'm going to keep my presentation fairly non-technical in nature, I guess, and sort of gear it towards showing you some of the types of things we do with stream banks, some of the practices, procedures, inventory procedures, and things that we use. And I tried to kind of estimate maybe how many of these I'd worked on over time. And I came up with maybe at least 600 projects that we've done in Southern Illinois, all on private land. So some of the photos you'll see today are, on private lands, and all of them will be on private lands. I think there might be 1 or 2 exceptions, but in general, we work with private landowners on conservation work. And I'll talk a little bit about the funding too, maybe at the end if we get a chance. Let's see if I can get this going. All right, so today's topics, we'll talk about some of the stream bank issues we have in Illinois and some of the causes of those, some of the root causes, how to work with streams, and that's going to be an important thing you keep hearing over and over, how to work with streams to achieve a balance. We'll talk a little bit about this vegetative versus structural practices, when is each one appropriate. And then we'll show you some examples of cost-effective structural practices for both stream bed and stream bank work that we've used on rural Illinois streams. And this is primarily going to be targeted toward rural streams. When you get in urban areas, the rules are a little bit different. We'll mention that a little bit in the presentation, but the photos you'll be seeing are in rural areas of Illinois. Well, Southern Illinois sure has its share of stream bank issues. Almost every stream has some sort of degradation or remeandering problems, or we've got some of the most notorious examples too of what can happen with streams when things are done incorrectly, I guess, from the start. One example we have is in the Cache River Basin, which is at the very southern tip of Illinois. And in the early 1900s, a project was done in the Cache watershed for the logging industry near Karnak to transport lumber to the Ohio, straight to the Ohio. And this Post Creek cutoff was dug to transport things straight to the Ohio, bypassing this entire lower section of the Cache River. And the Cache also used to dump into the Ohio here, north of Cairo. In the 1950s, a channelization project was done to divert the Cache for reasons of flood control in Cairo into the Mississippi. So that's one of the, it's the only river that's watershed used to be in the Ohio and now is in the Mississippi, I guess. But there's sections of this channel where flow goes both directions depending on storm events, and most of the flow from the upper Cache River now goes down the Post Creek cutoff. Most of the flow from the lower Cache River now goes into the Mississippi. So those channels that were once originally dug 30 feet wide, 10 feet deep, now they're over 200 feet wide and 60, 70 feet deep. If you go down to the town of Grand Chain, you can take Tick Ridge Road, and there's a bridge that crosses the Post Creek cutoff, and you'll know when you cross it because it doesn't look like any other stream you'll ever see. The bridge is not super wide, but when you see how deep it is there, you'll know instantly that you're in the right spot. We've had channelization of streams, of course, in Southern Illinois. This has led to a lot of long-term issues that we still deal with today, whether it's for mining or other industries. It would take long sections of the original river channel, which you can still see in a lot of aerial photography, and channelize it into a nice straight drainage ditch. And so they took the gradient that was in this length of stream and put it in this length. And when you change the gradient of the stream, we'll talk about in a minute, you upset the balance, and the stream responds certain ways. For instance, you know, in this 1,000 feet of channel, the channel slope originally with the sinuosity, it was a meandering channel with a sinuosity of 1.5, and that gave it a slope of about 3.3 feet per mile. Well, with the channelization, the valley slope itself is about 5 feet per mile. So if you look at how much that actually increased the bed slope of the channel, it's a 50% increase in the channel slope in that region for this stream, which the stream is going to respond to. So, you know, many folks that we talk to in, you know, in rural areas, landowners, you know, they're convinced their problems might just be over if they could channelize or cut off oxbows or things like that to prevent channel meandering. That can sometimes trigger worse problems other places. So anytime you're changing the bed slope of a channel or things about the cross section that we'll talk about in a minute, then that can trigger other things to happen. So knowing about the channel before you start any type of project is important. And of course, Illinois is not the only place that has channel issues and problems. I mean, just take a look at the Los Angeles River here, a photo of a river that's been not only channelized, but concrete paved, not the bottom only, but the side slopes. So it's a 100% engineered channel at this point. And for many reasons there, of course, it's in a highly urbanized area. But when we talk about stream banks today, we're going to talk about the channel evolution model. And it talks about the different classifications of streams and how they respond to events. If they respond to channelized sections by degrading, lowering the bed first, because a stream's natural tendency is to want to decrease its own slope by downcutting. Then in class 4, in the stage 4 of the channel evolution model, you get widening starting to happen as a byproduct of the stream getting deeper. Then class 5, maybe the stream has stabilized the bed, but you can still have widening. Then you kind of reach this new phase of quasi equilibrium until something else happens in the watershed. But you've reached this stage of equilibrium where there's a new bank full height, a new floodplain that's formed inside the channel. So we'll talk about channels that show that. So when we're doing field inventories, we're looking for signs of unstable incised streams, those indicators that we're looking for in the field. High steep banks, obviously that's one immediate note. Rotational slumps in the channel where large sections of it are sloughing off. Overhanging vegetation where the channel top width has gotten wider. I'll show you an example of that in a second. Exposed tree roots. One of the things I look for right away is no sediment deposits or natural riffles, no point bars or naturally occurring riffles in the stream that might tend to occur, you know, about every 10 bankful widths. You won't see those in channels that are incising. And nick points, I'll show you a photo of one of those here in a minute in the channel bed. So those are some immediate indicators of where the stream is in the equilibrium process and where it is in that channel evolution model. So this is an example, right? Tree roots don't grow in the air, so that's an indicator that the channel has widened and some of these trees are hanging on for dear life here. One of the indicators that we're looking for when out there doing inventories. We'll look at the soils too, because the soils greatly affect the channel's ability to respond, and it's even more complex when you have a different soil type in the higher part of the bank versus the bed material. Sometimes bed material can be very coarse and then have much finer sediments up higher, and that complicates things as well. Or maybe we'd see some sort of nick point in a section of stream where the head cut is going upstream in the channel, and as this channel struggles to get itself at a more stable grade, it's eventually going to affect the banks along the way too as the channel bed gets deeper. So some stream bank issues are actually start out being stream bed issues. You've probably seen this if you've looked at things like concrete box culverts and you see things like this at the downstream edge. You can bet that when that box culvert was installed, that the floor of the box culvert was nowhere near, it was close to the actual channel grade, and now the channel itself is eroded to be nowhere near where it was. Here's another example. This is, you see things like this fairly common. That's just a classic example of some down cutting that's occurred over time. And there have been down cutting in almost every channel to some extent in Southern Illinois to help reach new equilibrium based on new land uses, different runoff patterns and rainfall patterns and all types of things. So it can lead to some other issues too at bridges, of course. You know, here's an example of a railroad bridge in Vaughn County that has exposed piling now because of all the down cutting that's occurred. So we're looking for those indicators in the bed for stage 2 channels that there's, or stage 3 channels, 2 or 3, that there's active down cutting still going on. If we have field indicators that there's down cutting in the bed, then that can sometimes affect what we would do on the bank. And we have practices to try to stabilize the bed. After the bed, once again, you get into stage 3 and 4 channels, the channel's starting to widen. You get things like this happening where vegetation alone itself is not able to stop channel migration patterns. And it's trying to reestablish some meander pattern, and it's undercutting vegetation that's on the bank. That vegetation, especially tree roots that tend to hold the soil in place, wind up falling into the channel. Then it continues on its path. So you can have channels that look pretty rough, and they don't get stabilized until they're done down cutting and done widening without intervention. So that can lead to those kind of tree issues that you see on the bank. So maybe someone thinks that just it's a velocity problem against the bank that's causing this tree to get undercut and erode, but it could have started as a issue with the bed of the channel and some re-meandering that the channel's trying to do, and it may have just undercut this tree and allowed it to fall in. So in a pasture situation, we have this too. A lot of times we'll look at stream banks in pasture where cattle have aggravated the problem too. Here you kind of see a start of a rotational slump that's developing in the channel, and you can see, if you have a large enough screen, hopefully, that there's a definite difference in soil texture and properties here on this outside curve of the channel. It's developing this point bar here, and the elevation and locations of these point bars are a key indicator to us too that we look for in the field. Then as you get further into the stage 4 channels, you're going to see these point bars developing and depositional material starting in parts of the channel. One side could still be widening as it's finishing its meander pattern. And then you can reach this stage of quasi equilibrium where it's actually transporting and depositing some sediment in the channel, the bed load from upstreams being redeposited as gravel bars, point bars, those types of things, and you're getting a more stable situation long term. And it's sort of reestablishing its own floodplain at a slightly lower elevation. So this can happen even within the channel banks themselves, where it puts point bars, where it tries to reestablish a new bench inside the channel banks, is all indicators of down cutting in the past and indication of the channel evolution model stage. So sometimes you don't have the luxury of space, especially in urban areas. If you have a down cutting stream and there's some important utility or something to protect here, you may not have the luxury of allowing the channel to naturally adjust or make smaller subtle changes to what's going on. You know, if this stream is only 5 feet from your back deck, that's not a lot of spare room. And if it's your yard that it's taking out, that's a different story than most of the sites that we work with. A lot of times those do require much more expensive treatment methods to just entirely prevent from getting any closer at all. You know, maybe you installed some fairly elaborate retaining wall or something, and now this down cutting channel, rotational slumps and things are threatening that retaining wall. So those are a little bit different story. Or if you have a site where you've got a public road right next to the channel, and now there's a 12-foot drop off right off the channel, right off the road into the channel. That's the case in this one. So let's talk a little bit about stream dynamics. And I'd like you to begin thinking of streams as transport mechanisms for both water and sediment now. So that's the way we think of it. They're there really to transport two things. Everyone understands and realizes that they're there to transport water, but they also transport sediment downstream. Sediment that's eroded from the watershed, and that can either be allowed to be conveyed to an outlet, or it can be deposited somewhere along the way. A lot of times these are significant sources of sediment to watershed lakes or other things downstream, maybe even the primary source in some cases. Some of these sites we work on can have hundreds of tons of soil per year eroded from the bank. And it's almost directly deposited in the channel corridor where it's easily transported downstream, where it affects aquatic organisms and all types of things. In the uplands, you know, we use models like Russell 2, which is an erosion prediction model for cropland and other areas in the watershed. But when you talk about the stream corridor, we talk about sediment delivery ratio and its ability to take the sediments that it receives and transport them downstream, or to transport eroded sediments from the bank downstream. Even sometimes cleaner water or any change at all, even the fact that the water is cleaner, can give streams more potential power to pick up sediments along the way. So everything is part of a balance that we'll show you in a second. Also, another thing we have to convey to landowners is it's against the natural channel forming processes and forces to have channels that have uniform slope, uniform cross section, and are straight. That's not how natural channels form in sedimentary and alluvial soils, and any channel that has a uniform slope, uniform cross section, and is straight either has an extremely low gradient or it won't have that plan form for long. Because in general, we'll show you on the next slide how streams form, but trying to keep a stream a uniform slope, uniform cross section, and straight is always going to be working against the stream. What we're trying to do with our stream restoration practices is understand how to work with streams and know what they're doing. Natural stream channel stability is achieved by allowing the river to develop a stable dimension, pattern, and profile, such that over time channel features are maintained and the stream system neither aggrades nor degrades. That's when a stream becomes in balance. And there's things we can do to help that along. So we talk about Lane's balance, which is this balance that says that streams will naturally balance based on 4 factors: the flow in the stream, the slope of the stream bed, and that's going to balance against the sediment volume and particle size of the sediments, which is a complex process, but at least in general, you can see that as the stream slope gets more steep and you move the lever arm out on the right hand of the balance, then it's going to tend to degrade the channel. And so that's just a way of sort of expressing those relationships that we look at in streams. Another thing maybe a lot of folks don't realize is that a lot of the channel forming discharges, or the flow events that happen that tend to form the shape of the channel, there's research, not just only this, but many places that say that 90% of the sediment is transported in streams by events that have a return interval less than 5 years. So it's not those 100-year storms or 25-year storms that's causing the shape and effect of the channel overall. They may temporarily relocate parts of it or have some effect on them, but in general, the sediment and other types of things are carried by smaller events, anywhere from the 1 to 5 year storm or flow event in the channel. So this is an example of different channel geometry things. We talk about natural streams. We talk about riffles, which are shallow areas where water flows more quickly, and then pools, which are deeper, slower flowing areas. And a natural channel will have a series of riffles and pools. And as this meandering pattern exists, you get this helical flow that comes along the bank, and interrupting this helical flow is one thing we can do to move the channel bank out a little bit closer to the edge of the channel from where it's trying to erode. And then you can see from this one, this is a profile of a channel showing that you get these areas of riffles, areas of pools, then a riffle, then a pool. This is what a naturally stable channel planform looks like in most cases. And those tend to happen about every 8 to 14 bankful widths or channel widths, top widths. So that's another sign that we look for when we're doing inventories. If I talk about the foul wag later, that's just the deepest part of the channel. So if I plotted a line that showed the deepest spot throughout a channel, that's foul wag. And I'll talk about point bars a little bit. Riffles we talked about in pools already, so those are some of the natural features. Okay, so what's our goal of stream bank restoration? It's just to move the stream towards equilibrium while meeting the project goals. So streams often do inconvenient things. You know, the landowners come into our office and bring up, this channel has taken out 2 rows of corn every year for the last 10 years and it's getting worse, or things like that. So we have some project goals that we want to try to meet, and we want to work with the stream to do those. We don't want to use cookbook solutions because you don't want to wind up disrupting the system even more when you're trying to fix the problem. So our goal is to work with natural processes and know where the stream's going, and to the extent possible, let nature finish healing the banks. You know, in an urban area, you might have the luxury of really doing an engineered solution that would involve all the way up to the top of the bank, different plantings or other things. That would be just cost prohibitive in most rural areas. So keeping the cost down is a very, very important factor, and it guides what we do in a lot of rural areas for stream bank restoration. So let's talk about the role of vegetation. Can a stream be stabilized by planting just a riparian buffer zone or things? As we talk about some of these stream processes, you understand that they tend to happen towards the bottom of the actual stream channel, and vegetation up high on the bank often doesn't really do much to help that. Trees can to some extent because their roots tend to stabilize the soil, but you can see that a lot of these degraded channels we've shown, trees have not helped at all even. So vegetation's really only going to stabilize a stream bank when and only when a stream is near its state of equilibrium. So only for streams near equilibrium would we try to use vegetative means. And here's some of the reasons. Vegetation doesn't do anything for bed degradation, which is the main problem in most streams in southern Illinois for sure. So we can't plant vegetation in the middle of the channel, won't survive. So not the types of vegetation that we want surviving. Also, vegetation alone doesn't provide that hard toe needed to control lateral migration of the channel. So if we're trying to keep erosion patterns out of a field or in check, a lot of times vegetation is not enough to do that alone. A lot of the biodegradable materials are fairly short-term fixes for toe protection, so we have a few slides showing that in a second. And we do want the natural vegetation to play a role, but its role is that natural vegetation will reestablish if the toe is protected and our velocities are in check where it's trying to grow. So this is an example of a vegetative measure where we have a core log that's staked in place with wooden stakes, and there were some landscape plantings behind it, and those can be effective in some cases. And depending on the channel evolution model stage of the stream, those can be effective. One problem is, they're all usually temporary measures. So eventually you wind up just relying on the native vegetation for your protection again. And native vegetation wasn't preventing it from meandering or something before. So this is an example of a project after 5 years. There are things you can do to harden up or do in combination with vegetative management, like you can use practices like these Ajax, which can be installed at the toe and then rely on vegetation above that. And that's a simple version of what we're trying to do on some of these larger rural stream banks. So this can work in an urban area, and we're trying to recreate this on a larger scale and larger streams in rural areas. However, I have to admit that the use of hard materials has its issues as well. Let's say in this channel, we decided we were going to use rock riprap to just put all the way up to the top of the bank. Because you've decreased the roughness coefficient of this bank, now the thalweg, the center of the channel, and the flow velocities are going to be concentrated more towards the area of the improved part of the channel. And you may even get a gravel bar over here, as a lot of the velocities and things are concentrated against that. So if your material goes down far enough, that's fine. But if it doesn't, we'll show you what can happen. So you spend a lot of money and you put riprap up here on the top of the bank and thinking that's going to really solve my stream bank problem. Only now you've just shifted the velocities and things over this direction. The channel has readjusted in shape, and it now is undercutting the protection that you paid to install. So here's an example showing how the velocities can now be concentrated over where this protection is. And that's not necessarily a bad thing. It can add diversity to the channel. It can add this riffle pool sequence to the channel. So as long as your protection is deep enough and you know that it's in the right place, then that's not a problem. Where it is a problem is if you try to use some hard armoring sort of method, like these are rock gabions. These are wire baskets filled with rock and laced together. They're laced together and then filled with rock and then closed to make a rock wall. Well, this got undermined by the channel because now velocities underneath the gabion wall have caused the channel to erode so much that now the wall is leaning and failing. Well, here's another one where gabions were used, and then in addition to that, someone saw the future and decided, well, we're just going to add some concrete in there too. But you can see that the channel has once again shifted and undermined all the bank protection. So in general, we find that people spend a lot of money on bank protection up higher on the bank because they're not addressing some of the root causes of what is causing the problem. And this may actually be contributing to the problem more now, because the more concrete and smoothness that they add to this channel, the more it wants to downcut near the practices that have been installed. So we always do a fairly extensive inventory, including engineering surveys, anytime that we have stream banks that we're working with. We'll take up and downstream cross sections. We'll look perhaps for a half a mile downstream. We look at historical imagery. We look at the plan form and how it's changed over time. We look at point bars. We try to determine the density of point bars to see how long they've been there. All these types of field techniques are actually used by us in designing the practice and considering what things we might do. So I want to talk a little bit about riprap stone structures, and most of the efforts that we use in rural streams are these riprap stone structures, because they're an economical solution to working with streams, because they do provide some flexibility, they're easy to install, and relatively low cost. And some of the stream dynamics of using these hard point type structures can be mitigated. Some would say, well, you're putting riprap in the stream channel, that seems awfully structural. Although it might seem invasive, stopping the massive amount of soil erosion into the stream corridor that's happening from the stream bank and stream bed erosion going on continuously for years is a major benefit to everything downstream, the aquatic life that's in the stream now, And it's an ability to try to put the stream back more in balance through structural measures. And also we can design these measures themselves to help mitigate and improve even some aquatic life in the channel. We can try to recreate this riffle pool sequence. And so I'll show you some examples. And when I talk about riprap stone structures, this is not what I'm talking about, right? This is not rock riprap. This is not what to use. There are certain limitations permit-wise that you can't use certain things. Certainly we don't ever encourage anyone to use broken concrete, TV antennas, let's see what else we have, a chimney, a steel pipe, all kind of concrete culvert. These have all kinds of problems that can cause worse issues. Anytime you have a flat planar surface that you put in the stream corridor, it tends to act almost like an airplane wing, and it can cause velocities to increase in that section. So definitely not what we're talking about. What we are talking about generally is a poorly graded limestone riprap that's available and that can be placed by machine. And the size of those we'll talk about in a little bit when we talk about materials and costs at the end here. So there's really 4 major structural practices that we use fairly often in stream banks in rural areas. So I'll talk about the rock riffle grade control structures. These are structures for stabilizing the channel bed. They add the riffle pool sequence, they allow fish passage, and they try to recreate and stabilize and provide a stable point for overfalls to happen in the channel where they can be protected. Longitudinal peak stone toe protection is for channel stage model 3 or 4 channels. And this is an effort to stabilize the bank itself. So it's a lot of times used in conjunction with rock riffles. When you stabilize the bed, now you can work on the actual bank and perhaps protect something that's trying to meander into some place that you don't want it to. Stream barbs are another one too that we use for stream bank protection. And then finally Benway Weirs, and we'll talk about those. That's probably the least, these are probably in the order from the most commonly used at the top to the least commonly used things we recommend on the bottom. So a rock riffle grade control structure is an engineered structure of rock riprap where we try to stabilize the bed by putting in a series of riffles in channels that don't now have them because they're down cutting. So we try to recreate this riffle pool sequence in the channel, and these allow the dissipation of energy on their downstream slope. And it has a 20-to-1 downstream slope, so it does allow for fish passage, and it also aerates the water, provides aeration, and try to recreate that natural riffle pool sequence. They are keyed into the bank of the stream bank on both sides, and they do have a V-shaped crest, slightly V-shaped crest. And so we typically save the largest of the stones to be the crest stones and try to have the contractor place them in a crest, V-shaped crest, so that flow can go through the middle of them first. It's a very subtle crest. In this case, this is one that's been installed for quite a few years. Here's one you can see in a very degraded channel that a lot of overfall is being taken out of the channel at these riffle locations. So these are generally spaced anywhere from 75 feet to a few hundred feet apart. So that depends on the channel width and the channel geometry. But we space these, not always at even spacing either. Sometimes they are 75 feet for a while and then they'll switch to a longer spacing or more. But it's an effort to recreate this riffle pool and give it a protected place to actually erode. Sometimes the crest of the riffle actually would almost back water up onto the toe of the previous one upstream. If we need that level of protection in the channel, we can engineer a system where the stream is actually at low flows backing water all the way up to the previous riffle. So this might be what it would look like over a long-term setup where you can just sort of see the coarse stones, and they almost seem like a natural rock riffle that you'd find in a channel, only it's kind of an engineered solution to allow grade stability. The second practice I'll talk about here is longitudinal peak stone toe protection. It's for stage 3 or 4, and this is primarily for stream bank erosion. So the goal is to protect the base of the bank to prevent undercutting and to not use any more rock than you have to. It would cost a fortune, in this example, and not be necessary to put rock riprap the entire height of this bank all the way around. It would cost 5 times as much or more to buy that much rock. Really, down here is where you need the protection. And then the role of vegetation is that behind these, vegetation can begin to grow and fill in and be at a stable location where it won't get eroded. So it protects that area below the water line where you can't get vegetation to establish. And it creates a new level bench where vegetation can establish. So here's what it looks like right after it goes in. It's a peaked stone because it's sort of in a peaked windrow of rock, I guess you would say. And we'll talk about sizing in a little bit. And then every 75 feet or so, it'll have these keys that go back into the bank. This is to make sure that flows don't get behind this windrow and erode behind the peak stone protection. Or here's maybe one looking upstream at a site where you can see the keys a little bit better and how they go in. And you notice that this is just slightly higher than some of the point bars that are just beginning to try to form over here. So this was a field that had a tree line corridor. These trees that you see down here, this was trees all the way around to here. And they're all gone now because of lateral migration. And we're gonna try to reclaim some of that and establish the new bank line to be here. The new center of the channel will be out here. And fortunately, we have Google Earth now. So a lot of our projects, we can see on Google Earth. So here's a Google Earth imagery of that project. Here was 1 year after we installed it, or probably not even a year. This was taken in the winter, it looks like. So you can see how we installed it. The flow is going from the top of these pictures to the bottom. And then just 3 years later, this photo was taken. And now so much vegetation has grown. Really, if it's working right, it's really hard to find the rock after a while. And that's kind of hard to believe, but if you're trying to work with streams and you're doing what they already want to do, then they can stabilize themselves quickly, and this vegetation can grow back quickly behind what's already been eroded and reestablish this tree line bank here that was gone. In addition to this, we did have a riparian buffer that we did as part of the Conservation Reserve Program, I think, in this, if I remember right. So that's an aerial view of one. Well, here's another one on an actual drainage ditch where this was the same way. This row of trees extended all the way to the bridge, which this photo was taken on. And this bank was nearly vertical. It was so, it's probably about 10, 12 feet or so from the bank here to the bed of the channel. And it was so steep I couldn't even climb out of the channel except to just select places. And this is taken after only 1 year. So we put the peak stone in here, and you can see that plants are reestablishing, and eventually we'll have trees and vegetation, larger vegetation established. And we'll let what native plants grow up in here. We're not doing any actual landscape plantings. Once again, that just adds to the cost. So a lot of times it's difficult to do any kind of plantings that survive too. So well, here's another one sort of in the late stages here after the fact, and you can tell that it's starting to be stabilized, and what was once an eroding bank now has the channel in check, and point bars starting to develop out here. This point bar didn't exist in the past. Here's one not too long after it was done. So you can see that this windrow of rock has trapped a whole bunch of sediment and actually made new sediment here between the peak stone and the bank. So all the sediment's been trapped, and will now be the basis of the new vegetation that grows. So. Same here, just to show you some of the sediment trapping that happens behind these during some storms. These next pictures are a series of the peak stone in a bridge in Madison County, and this is right after it was installed. This is less than a year after it was installed, and this is the following year. And then several years later, this is what it looked like. So some of these photos come from Wayne Kinney, who some of you may know from Midwest Streams. He took these photos. So I'm going to move on to stream barbs, which is for stage 4 streams generally. They are angled upstream, so they kind of look like Benway Weirs, but they're angled very much upstream, and they kind of form a hydraulic stream break. So they're taller than Benway Weirs, which we'll talk about in a minute, and they have this sloping crest down into the channel. So it's a real tight angle with the upstream bank. So water comes in here, gets trapped, and kind of has to roll over back towards the middle of the channel behind each one of these. So in lieu of putting something for the entire bank line, we can just maybe put a series of these structures depending on the radius here. And we can heal this with very little rock. Here's another photo right after one was installed, just so you can see this sloped crest that they have that goes about 2/3 to 3/4 up on the bank and then is angled way upstream. Upstream would be in the right-hand direction in this photo. Or here's another one that we're looking downstream in this photo. So you can see that water will form a dead pocket behind these and tend to roll over this towards the middle of the channel. And this point bar will probably go away after this has worked for a while. Here's some that have been in place for a while and shows you a little bit about how they work over time. And another one that's a little bit further along, same channel. Benway Weirs we don't use too often anymore, but their purpose is similar to stream barbs. They have a flatter crest, and they capture flow behind them and release that flow at perpendicular direction to the Benway Weir. So they're put in not at a 90-degree angle, but just tilted slightly upstream so they can angle the flow away from the bank. So streams that have a natural width and have point bar material that's easy to move, those are good candidates for Benway Weirs. And we don't have a lot of those, but we do have some in some of the counties, so we have used these before. We do probably a few projects every year with them. So this would be after they've been installed for not too long. The toughest part is, getting these crest stones all level and lined up so that one of them doesn't get broken through. They involve a little bit more maintenance than the stream barbs, because if you get water flowing through them to create a void in them, then they have to be repaired with some O&M. So here you can see and give an idea how the flow is being redirected perpendicular to the weir, and the stream bank here will be healed. There we go. Okay, a few more slides before I end. I guess the rock sizing, we use IDOT grades of limestone riprap. Most projects use the 400-pound top size, meaning that the largest rock is 400 pounds. We also use some 6, which is the 1,000-pound top size, not too often for the largest types of projects that we do, and then gradation 4 in some smaller projects. We always want quality designation A, which means it doesn't have a lot of chert and different seams in it that can break apart with a lot of freeze thawing action, because these are subject to a lot of freeze thawing, and you want the best grade riprap you can get. We don't use geotextile. It's not necessary in this case. We want to place the riprap in places where it won't get undercut. And once again, we'll use the largest rocks to form the crest stones, either in a riffle or stream barb or something like that. So the costs. The costs for most of these practices vary from about $15 per lineal foot to about $50 a lineal foot of stream. And that just pretty much is based on the amount of rock that's required and the ease of access for delivering that rock. So it's a pretty economical way to not use very much riprap and have a really good result. We've tried all kinds of other structural measures. Like I say, when you don't have the luxury of space, you may have to try Gabion baskets, sheet piling, different walls or things like that. Those are more like $150 to $500 or more per lineal foot. But if your deck is 3 feet from the channel, that might be worth spending. So those are based on vastly different design techniques than we've talked about here today. So we've tried other things, lunkers, which are great for fish habitat, especially in urban areas. Those work. Sometimes we do those in conjunction with peak stone in urban areas or golf courses or things. Willow post plantings, different Ajax core logs. Some of those are better suited to urban environments, and some of them had long-term O&M issues like the willow post plantings and things. Hard to get survival out of those. So for permitting, it depends on the stream size and classification, but these are subject to federal and state permitting. There's a joint application permit that goes to Corps of Engineers, IDNR, and EPA, and I've just listed some of the actual nationwide and statewide permits that most of these fall in. So getting a permit is not usually difficult, except in extreme cases or certain waterways of the U.S. But it almost takes a case-by-case evaluation to talk to you about permitting, but in general, we've had no problem getting permitting for any of these projects. Okay, to wrap it up, just know what the channel is responding to before you decide how to treat it. I think too many folks think that just trying to channelize or pile things in the stream is going to stabilize it long term. And occasionally they get lucky and it works. But in general, it's best to understand how a channel is responding so you can decide what treatment to use. Keep it cost effective. And there are some channels that are so far out of equilibrium, it really does take extensive work to stabilize them. So you can always visit your local NRCS office if you have a stream bank that you're interested in. If you are in the bottom 30 counties, me or one of my staff will come out and look at it, try to make an evaluation of what's going on. And there are some programs that can provide cost share that we have, and also the state of Illinois has one too. So sometimes there's even assistance with projects. So that's all I have. So I'm going to stop sharing and take any questions you have.
Great. Thanks so much, David. We've already had quite a few really good questions come in, but I'm going to encourage anybody else from the audience, if you have questions, go ahead and type them into the chat box and we'll address them as we can. So one person asked basically, because you mentioned at the end about cost share available, what is the typical cost share percentage that a landowner gets, or that would be the landowner's responsibility? Kind of how does that work?
Depends on the practice, but it's not a percentage. It's a fixed rate. So it's so many dollars per lineal foot. Like I think one of them is $35 per lineal foot. So it doesn't matter if it costs you $60 or it costs you $40, you get a set rate.
Okay, great. Somebody mentioned they had farmers in their area basically cut all the trees along the bank. I guess wanting to know, you know, kind of how detrimental is that? And then that gets to a bigger question I had about a landowner's legal responsibilities for maintaining stream sides and maintaining that to prevent erosion. Kind of, can you speak to both of those there?
Yeah, that's it's never a good idea for our standpoint to remove vegetation that's near the channel. It's having some effect of stabilizing it, so we'd never encourage anyone to remove it. Your legal responsibility, if it's an organized drainage district, it could be different. That's a little complicated question to answer. In general, we do encourage you to remove trees that have fallen over from the stream corridor because they can cause erosion by redirecting flow. So we would encourage you to cut off and remove things that have actually fallen into the channel cross section. Okay.
That was going to be my next question. Somebody said if trees are falling into the stream, should they be removed? And how does that balance with, you hear a lot of stream ecologists talk about woody material in a stream and the benefits of that for you know, the insects and things like that. Kind of how do you balance those two almost counter ideas of removing them for erosion issues, but keeping them there for habitat?
Yeah, I guess if there are certain places in the channel, it could be beneficial. Just the way trees naturally fall, though, is generally not beneficial because they're not, you know, if they're oriented in a direction where they don't impinge flow or cause further erosion, then it would be fine to leave them. So sometimes if it's a large tree, we would just encourage someone to relocate it in the channel cross section. So
Okay.
I don't have a great answer, but
No, that's very good. So a couple more questions. Somebody talked about removing bush honeysuckle near a stream, and I'm assuming that's due to its poor ability to maintain soil. You know, there's I guess the bigger question would be different types of vegetation, and are there relative benefits to having them for stabilization?
we just tend to use native vegetation. If there are invasive species that are introduced in the channel, that's not good, obviously, and you could probably talk to that better than I can, but about removal of those. But we would not encourage invasive species in the channel. But other than that, we are encouraging vegetation to reestablish.
And in general, you said that's just you basically let nature take its course, and what comes in overall.
Yeah, unless we really had an invasives issue.
Okay. I'm trying to read through these. We're getting a lot more questions in. Somebody talked about beaver dams. When they form in a stream, should they be removed or encouraged or just allowed to be?
Beaver are one of those things, if we could only harness their energy for good. So sometimes it helps in some streams that are degrading, like the channel bed is degrading, they can help by almost providing a natural riffle. The problem is sometimes they build so high that they cause bank erosion. So if the stream is starting to get redirected by their work, then that's where you have to get involved.
Okay.
Otherwise, they can be both good or bad, just depends on the situation.
Okay, great. Somebody here mentioned they had the LPSTP, the toe protection.
Yeah.
And then after they had that done, the bank downstream on the same side really started eroding. And they wanted to know, is that normal, or is that just something that, you know, was a design issue?
It sounds like it maybe might have to be extended a little bit downstream. Generally, we extend peak stone on the same side until the channel kicks back over and starts on the other side. So maybe it needs to be taken a little bit further downstream, and that's something we can come and look at.
Okay, great. So one question that I had, I want you to address, if that's okay. It seems like some of these issues with the stream you talk about, it's either velocity or something coming from changes upstream, or incisement moving from downstream. It seems like some of these streams, to fix these problems or really kind of address them at the scale needed, it needs to be kind of large landowner collaborative issues that work against everybody that kind of owns aspects of the stream. And I just wanted to know, are there projects kind of out there that try to address stream restoration, stream stabilization, kind of at that larger collaborative issue or scale?
Yeah, we've had watershed scale projects where watersheds have had stream bank issues all up and down, and we've had some in Union, Jackson, several Saline, several counties where we've had watershed scale efforts to try to do stream bank projects. And if there's a local working group or something, or maybe a soil and water conservation district board or something is interested in getting more watershed scale effort, those sometimes can be given priority for funding if you get into an organized group and develop a plan for doing something on a larger scale.
Are there practices you can do in the uplands, kind of away from the stream, that'll have benefits to the stream?
I think riparian buffers are helpful, and also any practice that stores water, any sort of wascobs, terraces, those types of practices are usually helpful for streams.
Okay, great. I'm glad you mentioned streamside management zones. There was a question here about managing timber stands, forest areas, and maintaining streamside management zones, and kind of how important are they for maintaining your streams?
They're important enough for us that we'll actually help you enroll these areas in the Conservation Reserve Program many times, or a CSP program that we have. So we feel like they're important enough, streams are important enough to stay away from, that we'll help you and assist you establish those corridors and manage them. So.
Good deal. Okay. That's most of them that came in. I guess the last thing I would just ask you to speak on is if somebody has a stream, they're concerned about it, they see some of these issues, the best thing to do is just visit their local NRCS office, or kind of how do they go about seeking this assistance and how to resolve these issues they're seeing?
Yep, visit their local NRCS office, il.nrcs.usda.gov, or you can just Google Illinois NRCS and you can find where your closest field office is, and go in and talk to them. If they need to get the engineers involved in things, they will. So yeah, we're always happy to look at them. And the winter time is an excellent time for us to look at them because we don't have to deal with crop issues of accessing them. And the vegetation is, for the winter, it makes it much easier to kind of do the inventory in the winter.
Okay, great.
And snakes aren't out in the winter. So.
Right. Last question. I just wanted to ask one that came in. It was about different vegetation types as stream bank stabilizers. And I know you mentioned that quite a bit about vegetation is often not necessarily the end all for stabilizing, but they asked about trees versus perennial grasses versus forbs or shrubs, fibrous roots versus woody roots. Basically, what are your thoughts on if somebody did want to use vegetation to stabilize stream banks, kind of what's best, what's worse, those kind of questions?
Things with the largest and most fibrous roots possible, like trees, are the best, but I don't know. Since we don't usually recommend vegetative practices, it's hard for me to specify what vegetation is the best. We don't often, almost never, have a planning where we coordinate what we're doing in the bed of a stream or something with what vegetation we're putting up on top of the bank.